Go. Okay. Hey, Bio 375 class. We are here today to talk about lesson 6. And we're going to go through these and hopefully we can explain them in a way that helps. They're all very similar. And so for question 1, we talk about a disease, a rare genetic disease inherited in an autosomal recessive fashion. And the non-disease allele is a capital D, while the disease allele is lowercase d's. And suppose that this disease affects 1 in 150,000 individuals in a certain population. In all cases, parts A through D, please indicate your answers to 4 decimal places. Okay, so for part A, we need to find the frequency of the recessive D allele in this population. And so throughout this process, we're going to be using the Hardy-Weinberg equation, which is there's P plus Q is equal to 1, and then the Hardy-Weinberg is P squared plus 2 times P times Q plus Q squared is equal to 1, like so. So that's going to be the basis, and the P represents the dominant allele, the frequency for the dominant allele, and the Q represents the frequency for the recessive allele. So for question 1A, in order to find the frequency of the recessive allele, we do 1 over 150,000 because that's how many are affected. And so we know that there's 1 in 150,000, which is equal to this crazy decimal, 0.0000667 or whatever. And we know that this is the value that is equal to Q squared. And so, because Q squared is the number of affected individuals. And so we take that, and to solve for Q, we take the square root of that value, and our Q is equal to 0.00258, or 0.258%. So that's a very small percentage of people are affected of the D allele. And then the frequency of the dominant D allele in this population, you just use the P plus Q is equal to 1. So you'll do 1 minus, P is equal to 1 minus this, and so solve for P, and you get 0.99742, or 99.742%. And then C, frequency of the dominant D genotype in this population. So in order to find the frequency of the dominant D, homozygous dominant, that is equal to our P squared value. So we take our P value, which we got in part B, and we square it, and we get 9.9948, or 99.48%. And then in D, we're asked to find the frequency of the heterozygous genotype. And in this equation, we know that 2PQ is represented for the heterozygous individuals. And so we'll do 2 times P times Q. So 2 times our P value times our Q value gives us 0.00515, or 0.515% of people are heterozygous. So that's question 1.
All right, so for number 2, they're all fill in the blank, so it's pretty straightforward. So for A, the term in the Hardy-Weinberg equation that represents the frequency of the IB allele is, and I said Q because it's going to be the second one, and IA is going to be P. So the frequency of IAIB is going to be 2PQ because it's going to be heterozygous. So for B, 1 in 4,000 individuals in the population is affected, and the syndrome is represented by the, and then I said P squared, or 2PQ. And then, so if it's 39.99 out of 4,000, then the syndrome is represented by the, and I said Q squared, because it's going to be the recessive, because they said it's going to be recessive if they're affected. Um, so let's see. So the restricted phenotype is dominant over mallard and dusky. So the blank term in the Hardy-Weinberg equation best represents the frequency of the MD allele. And I said R because there's going to be 3 different alleles. So going on to E, the P squared term in the Hardy-Weinberg equation can represent the genotype of a duck with restricted plumage, which is going to be the M with the capital R. And then for F, I just found the rest of these in the slides. The human disease sickle cell anemia is the result of an SMP. And so G, it's going to be monomorphic as a term for a trait that produces one phenotype. And H, I'm not quite sure how to say it, Deems or Demis.
That sounds right.
Thanks. Is another name for a local population. And I, the MHC gene in humans, is highly polymorphic.
All right. Question number 3. For Marfan syndrome, and it's an autosomal dominant disorder. And so for the purpose of this problem, we'll assume that Marfan syndrome affects 1 in 6,000 individuals in the human population. So this one follows the same exact process that we followed in step 1 using the Hardy-Weinberg equation. And so in order to find the frequency of the non-disease allele in the human population, we simply take, so we know that 5,999 people are not affected in a population out of 6,000, in a population of 6,000. And so we take 5,999 and divide it by 6,000, as you see right here, and we get this value, and it's 0.999833, and that's equal to Q squared. So we take the square root of that, and we get 0.99992. So that's our Q value. That's the frequency of our non-disease allele. And B, what is the frequency of Marfan syndrome in allele in the human population? That's just the P value. And so we take 1 minus 0.99992, and we get P is equal to 0.00008. So again, a really small number. And then C for heterozygous, you just do 2PQ like we did in the previous equation. So 2 times our P value times our Q value. That gives us 0.00016. And then D, it's asking out of a population of 5 million people, how many heterozygotes are expected? So we just take this value that we got for our heterozygote frequency and multiply that by 5 million and get 800. So there's question 3.
All right, so moving on to number 4. So for number 4, it's asking, determine the allele frequencies for the R2 and R3 alleles. So what we're going to do is we're going to find the R2 first, and we're going to have to multiply. So the numbers under the column labeled numbers observed. So it's 135 for R2 genotype, which means that there are 2 alleles for each number observed. So we're going to have to multiply the 135 by 2, which gives us 270. And then we add 44 because we know that there are 44 R2 alleles in the heterozygotes. And that gives us 310. And then we divide that by the number of total, which is 376. And it gives us this number right here, this 0.8245, sorry. And so if we want to find the R3 allele frequency, then we can just subtract that 0.8245 from 1, and that gives us 0.1755. So for the chi-squared value, we can see the observed numbers on the question. And so to find the expected numbers, we have to do P squared times the total number of observed genotypes. So it's going to come out to 129.162. And then for the heterozygotes, we do the same thing. It's going to be 2PQ. So that's going to give us 54.986. And then for R3, we're going to get 5.852. So after we plug all that into the chi-square, we get 6.987 as a chi-squared value. And when you look at the chart, this value leads us to reject the null hypothesis. And it could be due to a lot of things. It might be sampling error. So that is number 4.
Cool. Okay, question 5. So in order to understand question 5, instead of me just reading off the process, I'm going to just explain like what it's saying and the Hardy-Weinberg equation really kind of quickly, and then I'll go through the answers that we got. So we're told that a particular gene controls the coat color in dogs, and it's controlled by 4 different alleles. And so we're given the frequency values, the allele frequencies for the 4 alleles. So this is a little different. We've been finding allele frequencies, but this one gives us them. And so I'll show kind of what I did. So I labeled for CCH, that, I don't know what that was, chinchilla. This one's chinchilla. This one's white dog with dark eyes. This one is a pale gray dog, and this is albino dog. So we're given these frequencies. So in order to find the homozygous frequencies for each of these, we won't have to, I mean, unless it specifically states, but all we would do is I labeled each of these P, Q, R, S. And if we want to find homozygous for any of these, we just square this value. And that gives us the homozygous frequency of that particular allele. If we want to find the heterozygous frequency, all we will do is do 2 times our 2 allele frequencies that we're given. So that's kind of the process of all of these questions. In question A, we're asked to find the frequency of a homozygous chinchilla and then a heterozygous pale gray dog, and it's heterozygous with pale gray and albino. And so all we do for that, and then also a homozygous albino dog. And so we'll follow that process that I just talked about. And for a chinchilla, we get 13.69%. For the pale gray dog, the C to the B, the CB, and then just regular C, we just do 2 times R times S. And we get 7.5%. And then C, for the albino dog, we just do S squared. We just do this value squared because it's homozygous. And we will get 2.25%. For B, if there's a population of 2,000 dogs, how many would you expect to have the pale gray phenotype, yet be heterozygous? So in order to be pale gray, but heterozygous, there's only one option, and that's CBC. And we already determined that allele frequency in this problem, and it was 7.5% or 0.075. And so we just multiply 0.075 by 2,000 and get 150 dogs. Sorry, I'll bring that into the light. For C, we're asked among a population of 5,000 dogs, how many would you expect to have the white coat with dark eyes phenotype, yet be heterozygous? And so for this one, there's 2 different options. We have the CD, CB allele combinations or the CD albino C combinations. And so we'll find the frequencies for each of those by doing 2 times each of their frequencies for the individual allele, and then multiply that by 5,000. So for this particular one, we get 575 dogs. For this one, we get 345 dogs, and we add them together, we get 920 dogs. So that's the answer to that one. Then among a population of 15,000 dogs, how many would you expect to have the CHCB or CC phenotypes or genotypes, sorry. And so we'll do the same thing that we did in the previous question where we find the frequencies of each one for this one and then multiply it by the total by 15,000. And so for CHCB, C, CH, and CB, we get 2,775. And then for the two albino, the CC, we get 337.5. We add those together and we get 3,112.5 dogs with either of those. Because there's an or, we add them together at the end. So there is our video. There are the questions. Hopefully that helped in some way. And that's all.